Okay, so now let's dig a little bit further into the diatomic molecule case, okay? So we just saw what happens if we assume that the molecule is like a rigid rotor, okay? So the distance r between the two atoms that make up the molecule is going to remain constant at all times, and the only thing that is happening to this particle is that it's just moving as a whole. The center of mass is moving, and also it's rotating about two orthogonal directions. But in reality, of course, this bond between the two atoms, it may change in distance, so the molecules may vibrate around their equilibrium positions like that. The atoms in the molecule. And what happens then is that the distance is not a constant. We define a variable, if you like, which is the difference between the actual distance between the atoms and the equilibrium distance. And we have to add a term to the Hamiltonian that describes how this distance or this difference of distance is changing over time. So remember, the Hamiltonian for a single molecule in our diatomic model is going to have a kinetic part, okay, which we wrote before, the rotational part, which we also wrote before, and there will be a new part, which would be these vibrations, okay? So if we want our model to be complete, we would need to add these vibrations, which we know are happening. So the way to model these vibrations is just a harmonic oscillation. So let's say there is some oscillation frequency, and here we put this r squared. Let's just try to use the same notation that I used in the lecture notes. So I am putting here some sort of reduced mass, r squared, and then there would be a momentum part, which is this pr, where pr is the conjugate momentum associated with the coordinate r. Okay, so from what we know from the equipartition theorem, if we are to calculate the average in thermal equilibrium of this vibrational energy, we see we have again the usual familiar structure. So it's 1/2 some constant and either the coordinate or the corresponding conjugate momentum squared. So each of these two are going to contribute with 1/2 of kT. Okay, and we have two of those. So what we have here is an additional kT. So remember that when you average the kinetic part, and this we did before, what you get is 3 times 1/2 of kT. When you go to the rotational part, there are two effective degrees of freedom, that is two terms of this form, and this gives you twice that. And now we have another twice contribution, okay? So what you get in the end is that you have the average energy per molecule being equal to 7/2 of kT. Okay, so that's it. And if you look at the total internal energy of 1 mole of such gas, of these diatomic molecules, what you have is the Avogadro number times this 7/2 of kT. Remember, Avogadro number times the Boltzmann constant equals the gas constant, so that's 7/2 of RT. And once again, heat capacity at constant volume would be the partial derivative of U with respect to T at constant V. Okay, in this case it's 7/2 of R. And by the generalized Mayer relation, again remember this is 9/2 of R. Okay, so just as a summary table of what we have learned, we learned that in the monatomic gas, okay, so let's just write it here, in a monatomic ideal gas, monatomic, let's write here CV and here CP, okay? So in the monatomic case, what we have is, what happened? Yes, there you are. Sorry, let me just position this here, fine. So what you have is 3/2 of R and 5/2 of R as CV and CP respectively. In the atomic case, which is incomplete model without vibration, so that would be the rigid rotor case, what you have is 5/2 for the CV and 7/2 for the CP. okay? But actually, when you do a more refined model for the diatomic molecule that also allows for vibration, which we know it happens, vibrations, then what the kinetic theory gives us is 7/2 for the heat capacity at constant volume and 9/2 for the heat capacity at constant pressure, okay? So, okay, the monatomic gas is the monatomic gas, but if we have to make a bet, okay, what is it that we are going to measure if we go to the lab and we measure the heat capacities of actual diatomic gas? For instance, the examples I put in the lecture notes, which would be nitrogen, hydrogen, and what else? That's carbon monoxide. So in these cases, if I go to measure the heat capacity, well, I would bet my money, given what I know, in that I will find these values. Okay, so because this model is more accurate. Okay, I know, or I would expect, however, that there will be some difference, because these molecules are not really classical systems, so they are described properly by quantum mechanics. But anyway, I would expect to see a value close to these values here for a diatomic gas. The thing that I write here in the lecture notes is that actually, if you look at these guys at 25 degrees, so like room temperature, you find values which are closer to this. Sorry, this is not what I wanted to do. So values which are closer to this too. Okay, so this is what you actually find for this room temperature for this type of diatomic molecules when they are very rarefied and you do a very precise and accurate measurement of the heat capacity. In this case, at constant pressure, you find this one. And this is puzzling because we know that this model should be more accurate. So does it mean that the molecules don't vibrate? They just go around rotating like a rigid system? Well, actually not, okay? And you can continue to make careful measurements in different temperature ranges. So if you heat up the system a lot and you look at the very high temperature regime where the gas behaves even more like an ideal gas, then you will find that for these examples here, you find like I think it's 5,000 degrees centigrade, you find this heat capacity at constant pressure closer to the 9/2 that you predict when you include vibrations. And even more puzzling is that if you take these same gases and you cool them down extremely low temperatures, like for instance, I have it in the lecture notes somewhere, I don't know, a few kelvins, right? So like tens of kelvins, I don't see it now, but very cold temperatures, you find this one, okay? Which is very striking because this one was derived for particles that cannot even rotate. They just move around, their center of mass moves around, and that's it. Okay, so this is a big puzzle, right? So let's just write the levels, if you like. Here, this would be the 5/2, and this would be the 7/2, and this would be the 9/2. This is heat capacity at constant pressure in this case, and here I'm going to draw the temperature, okay? So what I'm telling you is that I find, experimentally in the lab, values in, say, room temperature type of thing, say 25 degrees. Imagine this is not a linear scale at all, right? So it's like some sort of logarithmic scale or whatever, right? So maybe broken axis here and broken axis there. What we find is that you're more or less kind of over here in this regime. You find that at very high temperatures you are over there, and you find that at lower temperatures you are actually over here. Okay, and the actual heat capacity, if you plot it all, is going to be doing something funny like this. Okay, so this whole temperature dependence is absolutely not captured by kinetic theory, and really the explanation for it is that kinetic theory is just not right. Okay, it's a classical toy model for a quantum mechanical system, and if you want to get the full picture, you have to do proper modeling of the system. Okay, so this whole kinetic theory is okay, historically it was there, and it started statistical mechanics and gave a lot of insight into thermodynamics at the time. But we know now that molecules don't behave simply as a classical rotor that just vibrates and so on. So this explains the discrepancy, but still, we can have a qualitative understanding of what is happening in terms of this classical model. So the story will be like this: you are at room temperature, so the thermal excitations, which is the thermal energy that your system is getting from the environment at this temperature, is enough to excite the, say, the motional degrees of freedom. So it's just the particle moves as a whole, the center of mass moves around, it's not frozen, and also it rotates as a rigid rotor. But if you would like to make the molecule to vibrate, actually you look at the energy scale of these degrees of freedom. So this say, if you like, the frequency of those degrees of freedom is much higher. So you would need a lot more thermal energy to activate those degrees of freedom. So it's a bit like in this regime, you can think of the molecule really as a rigid rotor. It's not going to vibrate much. If you want to make it vibrate, you have to supply a lot more thermal energy. So you have to heat up the system a lot. Okay. And actually, if you cool down your system to extremely low temperatures, what happens is that even the rotations freeze out. So these degrees of freedom are completely frozen. And, you know, depending on where you are in temperature, the effective degrees of freedom that are active in your molecule are different. Okay, so instead of counting how many degrees of freedom there are in the Hamiltonian, you should gauge the relative importance of the different degrees of freedom given the temperature and given the say, if you like, the thermal energy, comparing that to the energy scales of the degrees of freedom that you want to activate. Okay, so that would be, roughly speaking, the story of the heat capacity. Now, the final thing for this video, before we go to the Maxwell-Boltzmann distribution, would be the rule of Dulong and Petit. And this is not for gases, but for solids. Okay, so let me just write it here. The rule of Dulong, or Dulong, let's see how you write this, Dulong and Petit. So what is this? Okay, you have a solid and you want to know what the heat capacity of this solid is. Okay, so what you do is you model the solid like a kind of lattice structure like that. So imagine a 3D sort of grid like this. You have a lot of atoms which are, you know, in some equilibrium positions somewhere in the lattice, but they also are allowed to vibrate. Okay, so they can move in 3D. They can make small displacements around their equilibrium positions in this 3D lattice. Okay, so the Hamiltonian that you would, in this case, this Hamiltonian is like a total Hamiltonian. Let's just emphasize it like this. The Hamiltonian for the whole solid would be a sum over a very large number of atoms. If you like, for instance, could be Avogadro number. And here you have the Hamiltonian of particles that are confined in some confining potential. You can approximate it as some harmonic potential, you know, any potential. If you look close to the stable equilibrium position, can be easily approximated by harmonic oscillator. So this is what we do here. So we say that Hamiltonian is, well, 1/2 of some frequencies squared and some masses, perhaps. Yes, I have masses in the lecture notes. Sometimes the masses are set to 1 just for simplicity. Just want to use the same notation, x, y, and z. It moves in 3 dimensions, but confined in this harmonic well. And then, of course, the kinetic term, which is 1/2mi, and then pi squared, let's say px squared. Let's just write the velocity. So, just px I squared plus pyi squared plus pzi squared. Okay, and the sum goes all the way up to a number of the order of Avogadro number. Okay, which is a lot. So what would be then the internal energy of this solid and corresponding heat capacity? Okay, so when you take the average here, of course, what you find is that you get n. So okay, how many terms like this are there? You can see, for instance, I just wrote one term out of this sum that contains Na terms, and this contains 6 of this type of terms. Okay? So there is a coordinate squared, 1/2 of that coordinate squared multiplied by some constant, and here is the same thing, 1/2 of that coordinate squared multiplied by some constant. Okay, so when you are going to average the whole thing, we know from the equipartition theorem that we would have 3 contributions of 1/2 kT coming from these guys here, and 3 additional contributions coming from these guys there, okay, KT. And because we have Na terms, well, it's Na multiplying this whole thing. That gives me the internal energy of the solid, okay? So let's write this out. So, okay, we have 6 of these things divided by 1/2, so it's 3 times Na KT. That would be approximation to the internal energy of the system. And remember that the Avogadro number times the Boltzmann constant is the ideal gas constant, okay? So again, the heat capacity in this case, because it's a solid, heat capacity at constant volume and constant pressure are roughly the same thing. We just take the derivative with respect to temperature. Let's believe that volume is constant in this case. What we get is 3R, okay? So that is actually approximately what you find in experiments. So it would be something like 20-25 joule per Kelvin per mole. Okay, something roughly like this, joule Kelvin per mole. Okay, so this is a kind of back of the envelope calculation to approximate the heat capacities of any solid. Okay. Of course, the reality is that solids have different heat capacities. They depend on temperature. They may have some volume dependence. It's a lot more complicated, but this is a rough estimate that you can use actually quite successfully to solve problems. And maybe remarkable thing to note here is that you are dealing with a solid, okay? And this R is the gas constant, the ideal gas constant. The solid has nothing to do with an ideal gas, but this ideal gas constant just appears there because of Boltzmann constant, okay? So fine, the last bit of this lecture that remains is to go back to this velocity distribution in the ideal gas of within kinetic theory and try to write out explicitly the form of that probability distribution. So that's what we are going to do next.